bit of an introduction. Reina is a current senior at Lee High School and joined my lab several months ago, where she's grown tremendously, not only as a student, but also as a scientist on a number of very challenging synthetic problems, which connect organic chemistry to chemical biology and drug discovery. Specifically, Reina has been working on various natural products, including our progress towards the total synthesis of a compound called withaferrin A, as well as analogs of andrographide. And today she's going to be sharing an intersection of two of the areas that our lab has been working on, fluorine NMR spectroscopy and natural product synthesis, as we approach the development of these prodrugs, of these fluorinated steroids. So Reina, go ahead and you're up to bat, go.
Okay, hi, I'm Reina Hong, and I'm a senior at Lee High School. Today I'm going to present my research on synthesis of dexamethasone and related fluorinated corticosteroid prodrugs. So this is a brief outline of what I'm going to be talking about today. I'll be going over an introduction of fluorinated drugs, prodrugging, details about our project, and some future plans. So corticosteroids can be generalized into two main types, glucocorticoids and mineralocorticoids. Glucocorticoids are widely used for their effects on inflammation, and an example is cortisol. And mineralocorticoids can help homeostasis and regulate blood pressure, an example being aldosterone. So corticosteroids have been in the market for a long time due to its potency. However, they are quite poor because of their short half-life and poor metabolic stability. An introduction to fluorination led to the discovery of fluorinated steroids, which are more highly potent, more selective, and much more metabolic durable. And in fact, 20% of the commercial pharmaceuticals are fluorinated pharmaceuticals. The first ever FDA-approved fluorinated corticosteroid was fludrocortisone, which was approved in 1954. And since then, lots of fluorinated steroids have been approved for proving to have better bioavailability, metabolic stability, and potency compared to regular steroids. Out of these, our project focuses specifically on dexamethasone, which was FDA approved in 1958. And it's very good for anti-inflammatory effects on chronic diseases. However, they're still way too reactive and metabolic problems still remain. So our goal of the project is to prodrug the steroid in order to improve its metabolic window and elongate its half-life. So I'll go into further detail later about the mechanistic part of the steroid, but here is a brief overview of how dexamethasone binds to the glucocorticoid receptors when it goes into the cell. The ketone in the bottom binds to tryptophan, and the hydroxys here bind to asparagine. So there are many ways of prodrugging, but to start off how a prodrug works is that it's usually a drug binded to a promoiety. And when it's binded, the prodrug is inactive. Through biotransformation, usually like an enzyme, it detaches with the promoiety and the drug becomes active. And on the side here, there are different properties that can be attached. But other than these, some other methods include disulfide-based prodrugs and cathepsin cleavable prodrugs. We chose to do a C11 oxidation, however, because it's more atom economical, has no potentially toxic byproducts, and is generalizable to the 11-hydroxysteroid scaffold. And a C11 oxidation is where a primary alcohol is converted to an aldehyde, or a secondary alcohol, which is, in our case, it is transferred into a ketone. We based our decision based on previous research studied about prednisolone. Prednisolone is similar to dexamethasone, other than the fact that it is not fluorinated, as you can see here on the C9 position. It was prodrugged into prednisone, which was FDA approved in, I think, 1955. Prednisone has a shorter elimination half-life compared to, longer half-life compared to prednisolones. And they used a specific oxidation called PCC oxidation, which uses pyridinium chlorochromate. So we actually tried different conditions for oxidation methods to find the best one, but the best condition proved to be the PCC oxidation. Other conditions either had poor yields or it decomposed. And to go into detail about how PCC oxidation works, the lone pairs here attack the chromium to form a CRO bond. The attack on the hydrogen, which attacks the oxygen, forms the ketone, and the rest of the PCC leaves. So we used PCC oxidation on dexamethasone. However, before that, we put TBS and TBDPS protecting groups on the top in case the method oxidized the primary alcohol. When we reran the oxidation with regular dexamethasone, however, it selectively oxidized the secondary alcohol to yield oxidized dexamethasone, which we confirmed by 1H and 19F NMR. This is a little more detail on how fluorinated steroids are metabolized in the cell. So the inactive oxidized dexamethasone, when it enters the cell, it binds with the enzyme, which is, in our case, is the 11-beta hydroxysteroid dehydrogenase. The enzyme will dehydrogenate the ketone back into an alcohol, and when it is released, it binds to the glucocorticoid receptor, or it is metabolized by the CYP3A4. In order to make sure that our oxidation method actually works, we tried other fluorinated corticosteroids, but still use the same PCC oxidation. We tried it on betamethasone, fludrocortisone acetate, triamcinolone acetonide, and fluocinolone acetonide. We also compared the TPSA values and the C-log-P values between the oxidized version and the non-oxidized version. And we found that the non-oxidized versions have higher TPSA, but it has lower C-log-P values. So our future plans include using HPLC assay to prove that the dehydrogenation works with the enzyme. We also want to do a little synthesis change on fludrocortisone because, as you can see here, it is missing an enol at the C1 position compared to the other fluorinated corticosteroids. And adding it here would allow us to, compare the oxidized state with the original compound more directly. Finally, I would like to acknowledge the rest of our project members, lab alumni who've worked on this project before, my advisor, Dr. Njoo, and ASDRP for providing us with the space and content to continue this research. Thank you.